Right, so this is, I think, the last video in the sort of aromatic chemistry series. It's been three. The first looking at the structure of benzene, second looking at the electrophilic substitution, specifically looking at nitration, and this one's going to be looking at the Friedel-Crafts Acylation. Before I start, just exactly as in the last one, because it depends on what order you're watching these, the key thing is the reaction that benzene undergoes, or the reactions, is electrophilic substitution. So this comes under obviously the family of mechanisms, which if you learn them and understand them, are fantastic ways to get some good marks. Within the electrophilic substitution, if it's nitration, you open yourself up to certainly a good 6 or 7 marks, and the same is true of the Friedel-Crafts Acylation. You've probably got a little bit less chance of getting so many marks because the formation of the electrophile carries a little bit less in so much of how many marks are available, but still you can get a good sort of 4 marks from it, if not 5. Electrophile, key thing, it's a lone pair acceptor. Obviously a nucleophile is a lone pair donor, and substitution is a direct swap at a particular point in a molecule. In this case we're talking about benzene, so if I draw benzene, often it will be around 1 carbon, where normally, just to expand on that, there would be a hydrogen. We would be swapping that hydrogen with something else, whatever that be. And that's the key part there, is we are swapping something with another part, in this case the electrophile. So, just like in the nitration reaction, it depends obviously which order you're watching these, or which order you've covered stuff. In the nitration reactions, we have to form the electrophile, and that is exactly the same in this thing here, which is the, I should write that down really, it's the Friedel-Crafts Acylation. So that's the key bit there, it's Friedel-Crafts Acylation. And it's the acylation part which refers to the electrophile that we're going to use. And in general terms, the electrophile comes from an acyl chloride, which reacts with aluminium chloride, aluminium trichloride. And so the reaction is going to be, and I'm going to do it as a general one, we would have some sort of RCOCl, or cockle group as I like to call it. That's your actually acyl chloride part there. Hence the acylation. Acyl chloride, that's going to react with AlCl3. And what we're going to do is we are ultimately going to take away that chlorine there. So we're going to end up with just RCO plus and then AlCl4 minus. That there carries a nice mark in an exam. And the key portion to this, oh, it's done that thing again where it doesn't scroll down. Oh no, I've gone the wrong way. I have no idea what I'm doing on this at all. Is that right? I don't even know anymore. Oh, it's not even the right thickness. I'm going with it. I'm not going with it. I'm going back. Is it that one? Yeah. Okay. Sorry, I probably should edit that out, but I probably won't. This here, in terms, is that too thick? No, it's fine. In terms of what this looks like, we've got an R group bonded to what would normally be that, which is our COCl, our cockle group in the acyl chloride. But I'm going to remove that part, and what we end up with is we end up with this. We end up with a positive carbon with the R group there, and bonded, with the carbonyl group there, basically with the carbon being positive. And this here is what is going to actually be bonding to the benzene. Just like the nitrogen was in the NO2 group, the nitro group, we're going to be bonding directly to this part here. So, the mechanism itself, quite straightforward really. The mechanism is exactly the same as the last one. So if you are happy with the last mechanism, it's absolutely no different. All we end up with, if I just put the pen near it, it just disappears. Much easier. There we go. So we have the same starting step. We draw our, I wish I could draw a good benzene. If I did, I'd be so happy. Circle in the middle. Always keep that circle. If you don't include the circle, you've instantly lost a mark because you've drawn cyclohexane. Depending on what type of molecule we start with, remember the nitration one, and I don't know if any of the examples I'm going to show you have this. They could give you a methyl group attached. You've got to obviously orientate things correctly. First thing, as before, now I would suggest here that what you do is you make sure, I would draw it as a as a displayed structure, as basically a drawn out structure, so you can make it really clear where the reaction's actually going, where the electrons are moving to, and where the bond is taking place onto. What are you doing that for? Just there we go. So that's our first step. Is exactly the same as the other one. From the delocalized ring there, touching the ring, arrow comes off, double-headed, it hits that. Next step, we end up with the benzene ring. Two parts now joined. We have a hydrogen and we have our COR. And then we have to have this horseshoe thing, which does not extend past there or there. Obviously, you don't draw those lines on. And then a positive portion within that. And then the final step is this here comes in, and we lose that hydrogen as per the electrons within the covalent bond there, falling back in, and this will ultimately reform. Can I scroll down? No, I can't. Of course I can't. Stupid thing won't let me. This will end up reforming the ring. Not required to draw the product unless it states that. Ring reformed, and now we have that bonded to it. So some sort of, obviously, basically phenyl ketone type thing going on there with the benzene bonded on. And that's really that. I believe here it's the aluminium, the AlCl4 minus is actually where the hydrogen goes, and I think you lose the chlorine and form hydrogen chloride. I can't remember definitely, but I think that's it. And so you get I think the aluminium trichloride there is reformed in this process because it loses one of the chlorines to the hydrogen in the production of hydrogen chloride. That's not required though for the mechanism. The mechanism itself just needs this step and this one. That's going to get you 3 marks for drawing those steps there. The equation is potentially going to pick you up, obviously another mark. And there you go. That is it really, Friedel-Crafts acylation. There's nothing more to add into that. I have got a couple of questions now, so as before, we'll have a quick whiz through them. Nice short video. Okay, first one is from June 2016, so a reasonably recent paper, but of the old specification, all the same. We can see there we've got this. Oh no, I thought I was going to highlight, but it hasn't. I'm just drawing circles. Where we had Chem 4, the old Unit 4, where the aromatic stuff was. I'll just show you what the question actually consists of, and the important bit here is 4b, where we've got X being this chloro acyl chloride thing, and we've obviously got the benzene ring there, and a reaction going on with the AlCl3 to form P. And it's what it's saying is to draw the structure of the electrophile formed by the reaction of X with AlCl3. Well, the electrophile formed is essentially, if I've got, well, that's our structure here, so we've got Cl, CH2, and then a COCl. So we've got Cl, CH2, and then it would normally be COCl. Remember, we lose the Cl and we just end up with the C there. So that's our electrophile, worth 1 mark. Not a huge amount there. They could do that in a probably linear equation format, but they've done it just to show the formation of the electrophile, which is fine. Just to draw the structure of that. Outline the mechanism for the reaction of the electrophile from part B1 with benzene, the preparation of P. So P's there, we can see there's nothing special about the benzene. We can add it really wherever we want. And there's the hydrogen chloride, as I said actually in my other bits. So it is the Al that's being basically acting as a catalyst in this reaction. So all we're doing is benzene ring here. Not got a huge amount of space. 3 marks though, fairly straightforward. That's going to come around. We're going to have our CO, CH2, Cl. In fact, you know what, I'm going to just, oh no, how do I get back to pen? Oh, there it is. damn it. CH2Cl. So all we're going to end up with is, next step, the horseshoe thing. Remember, to draw it correctly, we want the two things joined on, and we want here, we're going to have our CO, CH2Cl, and this is going to fall back into there, and that, as I said before, the AlCl4 minus, which is produced, is going to basically, you're going to lose a chlorine from that. That's going to take the hydrogen, produce hydrogen chloride, and reform the aluminium chloride, and therefore act as a catalyst. So there's your 3 marks there. Obviously, a little arrow in between. Nice. I'm going to ignore the bottom part there, which is about acid anhydride, I think it was. So this one, again, a very similar one. It's also question 4. This question is about acylium ions, RCO+. The acylium ion is formed in a mass spectrometry. Blah, 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 blah. We're going to ignore this first bit about the fragmentation. Here you go. Write an equation to show the formation of this acylium ion by the reaction of ethanol chloride with one other substance. Well, ethanol chloride is going to be CH3COCl, CH3-chiococcyl, and that's going to react with the AlCl3. We end up producing CH3CO plus and AlCl4 minus. 2 marks there. That's a ridiculous number of marks. I would imagine there the marks are going to be, because it doesn't tell you that you need AlCl3, so there's 1 mark for getting that correct. You could just write that and you'd probably get 1 mark, and then there's the correct equation is going to get you the other mark. Name of mechanism here, so name of mechanism is the acylium ion, electrophilic, that's not how you would normally write that, substitution. Mechanism exactly the same before. I will just check, actually, I know it's going to be benzene, but is it a weird one? No, it just reacts with standard straight old benzene. So, same as before, CH3 there, touching there. Oh, don't do that. No. Why? Where's my pen gone? How do I get back to a pen? P. There it is. I found it. That's going to react with that. Our intermediate step before our final product would be the horseshoe thing again. Positive in there. 2 things bonded on. COCH3, and remember that collapses in, reforms the ring. Bam, 4 marks. Thank you very much. Hopefully, I think that's quite a quick video. Reasonably straightforward, actually, once you've done the electrophilic substitution stuff, because you've got those 2 different aspects you can get it in with the nitration and the Friedel-Crafts Acylation. There's quite a lot of scope there for picking up marks. Once you've got it, as with all mechanisms, it's an easy one to apply to different situations. The key thing, as with the nitration, is to make sure that your original benzene doesn't have anything else bonded to it, which will dictate where your electrophile bonds to. And that's an important step that you need to make sure you do. Otherwise, hopefully it's been of some help. As always, just shout my own, blow my own trumpet. Twitter, get on, follow, all that stuff. If you want to ask any questions, that's your best place to do so. New website, mrerintoul.co.uk. Give that a shout, please. Otherwise, as I say, I hope that's been of some help to you.